In this portion of physics, there's two equations that you need to know. Q is equal to m times L, and Q is equal to basically MCAT, MC delta T. Q represents the amount of heat energy that is absorbed or released, and Q is measured in joules. It can also be calories as well. One lowercase calorie is about 4.184 joules, and a capital calorie is equal to 1,000 lowercase calories. Both are used for units of energy. Typically, joule is more common, but when dealing with heat, you might see calories or kilocalories. 1 kilocalorie is equal to 1,000 calories. M is the mass in kilograms. L is the latent heat. It could be the latent heat of fusion or the latent heat of vaporization. So if you're taking physics, you might see this symbol, LF, for the latent heat of fusion. In chemistry, you might see delta H sub F. But we're going to work on problems from a physics perspective. Now, what exactly is the latent heat of fusion and the latent heat of vaporization? Whenever a solid converts into a liquid, like ice goes into water, or whenever ice melts to water, that's what I meant to say, the energy that's required to melt ice into liquid water is the latent heat of fusion. You can also use it to calculate how much energy is required to freeze water into ice. The only difference is the sign might be negative instead of positive. The latent heat of vaporization is the amount of energy that's required to vaporize a liquid into a gas. In the case of water, it takes 3.33 times 10 to the 5 joules per kilogram to melt ice. So if you have 1 kilogram of water or 1 kilogram of ice, it's going to take 3.33 times 10 to the 5 joules to melt that cube of ice. If you have 2 kilograms of ice, it's going to take twice as much heat to melt it. The latent heat of vaporization for water is about 22.6 times 10 to the 5 joules per kilogram. So it takes a lot more energy to vaporize liquid water than to melt ice. As you can see, it's about 7 times more. Now, what about the other equation? Q equals MCAT. When should we use that? So you only want to use the first equation whenever you have a phase change. Whenever a solid melts into a liquid, or whenever a liquid vaporizes into a gas, or vice versa. The gas could condense back into a liquid, or the liquid could freeze back into a solid. But for the equation on the right, you want to use it whenever there's a temperature change. So if the temperature goes up or goes down, you want to use it. So M represents the mass in kilograms. Q is the energy. It can be in joules or calories. And delta T is the change in temperature in Celsius. You could also use Kelvin. The answer will be the same. And C is known as the specific heat capacity. The specific heat capacity for liquid water is about 4,186 joules per kilogram per Celsius. Now, what exactly does this number mean? It means that if you have 1 kilogram of water, it takes 4,186 joules to raise the temperature only by 1 degree Celsius. So, a substance with a very high specific heat capacity can store a lot of heat energy without changing the temperature much. The specific heat capacity for metals are very low, because once you add heat to a metal, the temperature increases greatly. Metals conduct heat very well. But in the case of water, if you heat it up, it takes a long time before the temperature goes up. So water is very good in storing heat energy. Now, what about the specific heat capacity for ice? For ice, it's about half of liquid water. It's 2,100 joules per kilogram per Celsius. And for steam, it's very close to ice. It's about 2,000 joules per kilogram per Celsius. Now let's work on some problems. How much energy is required to melt 450 grams of ice? What do you think the answer is to that question? So first, let's write the equation. We're dealing with a phase change. We're not changing the temperature, we're changing the phase of water from a solid to a liquid. So we need to use the latent heat of fusion. And whenever you're converting a solid to a liquid, you need to add energy to it. So therefore, Q is positive because you're putting energy into the system. Now let's convert the mass to the grams to kilograms, because the value for LF that we have is joules per kilogram. So to convert grams to kilograms, divide by 1,000. So 450 divided by 1,000 is the same as moving the decimal point 3 units to the left. So this is 0.45 kilograms. So now let's use the equation. So Q is equal to the mass times the latent heat of fusion, which is 3.33 times 10 to the 5 joules per kilogram. So as you can see, the unit kilograms cancel, and we're going to get the energy in joules. So it's going to be 149,850 joules. So that's how much energy is required to melt 450 grams of ice. Now to convert it to kilojoules, if you need to, just divide it by 1,000. So this is about 149.85 kilojoules of heat energy. How much heat is required to raise the temperature of 0.15 kilograms of water from 20 degrees Celsius to 50 degrees Celsius? 55. So this is a temperature change problem, which means we need to use the equation Q equals MCAT. And we're looking for Q. So we have the mass, which is 0.15 kilograms, and the specific heat capacity for liquid water, we said it was 4,186, and the units were joules per kilogram per Celsius. And then the change in temperature, so if we take the final temperature and subtract it by the initial temperature, that's 55 minus 20, we'll get an increase in temperature of 35 degrees Celsius. So now let's pay attention to the units. The unit Celsius will cancel, and the unit kilograms will cancel, which means Q is going to be in joules. So 0.15 times 4186 times 35. So it takes 21,976.5 joules just to heat up 0.15 kilograms of water, which is about 150 grams of water. So if you divide by 1,000, this is 21 point, I guess you can say, you can round it to 22. It's about 22 kilojoules of energy. How much energy is required to convert 3 kilograms of ice at 0 degrees Celsius to water at 30 degrees Celsius? So notice that we have a phase change and a temperature change. So there's two different Q values that we need to calculate. We need to find out how much energy is required to melt ice to liquid water, where the temperature stays constant from 0 to 0. And then we need to find out how much energy is required to heat up the liquid water from 0 degrees Celsius to 30. By the way, you need to keep in mind that ice melts at 0 degrees Celsius and water boils at 100 degrees Celsius. Now let's see how much energy is required to simply melt ice. So we need to use the latent heat of fusion. So Q is equal to M times L. The mass is 3 kilograms, and the latent heat of fusion for ice is 3.33 times 10 to the 5 joules per Kelvin. So we simply have to just multiply those two numbers. And this is going to be about 999,000 joules of energy. Now what about the amount of heat required to heat up water from 0 to 30? Now that's a temperature change problem, so we need to use this equation. Q is equal to MCAT. The mass is still 3 kilograms. The specific heat capacity of water is 4186 joules per kilogram per Celsius, and the change in temperature is positive 30. So the total energy required is 376,740. Well, that's not the total energy, but this is just the energy required to heat up liquid water. Now the total energy that's required to go from ice to water at 30 is the sum of these two values. So we need to add Q1 and Q2. And that's going to be 1,375,740 joules of energy. So this is the answer to the question. Now let's spend some time talking about the heating curve. So let's say if we have this particular graph, and we're going to have heat on the x-axis, that's the amount of heat that we're adding, and on the y-axis we're going to put temperature in degrees Celsius. So we're going to start with ice, let's say at negative 20 degrees Celsius. As we add heat, the temperature of the ice will increase. It's going to increase quickly. And then at some point, the temperature is going to remain constant. It's going to stay the same. And as you continue to add heat, it's just constant. And then if you keep adding heat, the temperature is going to increase, but with a different slope. And then eventually, the temperature is going to be constant for a long time. And then it's going to heat up with a slope that is very steep, but close to the original one. So what is going on here? You need to keep in mind that whenever the temperature is constant, that means that a phase change is occurring. Ice melts at what temperature? If you recall, ice melts at 0 degrees Celsius. So at 0, the temperature is going to remain constant until all of the ice cubes have melted into liquid water. So as you go this way, melting is occurring. Ice melts into liquid water. Likewise, if you go backwards, if you remove heat, liquid water could freeze back into ice. Now, once you get to this point, right in the middle, that means 50% of the ice have melted into liquid water. So you have 50% ice left over and 50% liquid water. Once you get to this point, it's 100% liquid water, no more ice. Over here, it's all ice, no water. Somewhere over here, like 1/4 of the way, you have 75% ice, 25% water. So as you progress, proportionally, the ice cube is melted into liquid water. And then the temperature goes up. So you're heating liquid water, and the temperature increases. And then the temperature is constant again. Liquid water boils at 100 degrees Celsius. So at this point, the liquid is vaporizing or boiling. So vaporization is occurring. The liquid is converting into a gas. Right in the middle, you have 50% liquid, 50% steam. Going back the other way, this is known as condensation. And then at this point, once all the liquid water has been converted to steam, the temperature begins to go up again. Now, why is this line so much bigger and longer than this one? What do you think the reason is for that? Now, do you recall what the latent heat of fusion and vaporization for water is? The latent heat of fusion for ice and liquid water is about 3.33 times 10 to the 5. And the latent heat of fusion for liquid water and steam, I mean not fusion but vaporization, it's much higher. It's 22.6 times 10 to the fifth power. So because the latent heat of vaporization is so much more higher, it takes more energy to vaporize liquid water into steam. And that's why we have a much bigger line here, because it's going to take a longer time. It requires much more heat energy to vaporize liquid water into steam. Almost 7 times as much. Now granted, my graph is not drawn to scale, but this should probably be about 7 times longer than this segment. Now what about the slopes? Notice that the temperature rises quickly in the case of ice, but for water, the slope is not steep compared to ice. It doesn't rise as quickly. And it has to do with the specific heat capacity. When the specific heat capacity is low, the slope of the line is very high, meaning that the temperature changes quickly as you add heat. The specific heat capacity for ice, we said it's about 2100 joules per kilogram per Celsius. But in the case of water, it's about 4186 joules per kilogram per Celsius. So it takes less energy to raise the temperature of ice by 1 degree Celsius compared to water. So that's why water is not as steep as ice, at least the slope for it. So the specific heat capacity and the slope of the line that you see whenever the temperature is increasing, these two are inversely related. A steep slope means that the substance has a low specific heat capacity. If the slope is not as steep, if it's more horizontal, if it takes a longer time to raise the temperature, that means that that particular substance or that state has a higher specific heat capacity. Now let's talk about energy conservation. Whenever we have a temperature change, that is in these 3 segments, what is happening as we add heat? Where is that heat energy going? Have you ever thought about that? Whenever you raise the temperature of a substance, the molecules, they're moving faster, they're vibrating at a faster rate. If it's a gas, they're moving with a much greater speed. So whenever you increase the temperature of a substance, you increase its kinetic energy, its energy of motion. So in those 3 sections that I circled, the kinetic energy of the substance is increasing because the temperature is increasing. Now what about during a phase change, when the temperature is constant? During melting or vaporization, we're adding heat energy, but the temperature is constant, so which means that the kinetic energy is constant. So what is going on here? Where is that heat energy going? Whenever you change the phase of a substance, you're changing the potential energy of the substance. Now let me explain. When ice melts into liquid water, you're breaking the bonds that holds ice together, the hydrogen bonds. And as you vaporize liquid water into steam, you're moving the molecules further apart from each other. And basically, you're changing the relative position of the molecules with respect to each other. Typically, when 2 atoms get closer and they bind, they release energy. But it takes energy to separate 2 atoms or 2 molecules and put them away from each other. Now, if you think about it, here's a good way to illustrate this concept. Think of gravitational potential energy. If you have a ball on the ground, basically attached to the earth, the gravitational potential energy is 0. However, to separate the ball from the earth, that is to lift it up above ground level, it takes energy to do that. You got to put in energy to increase the potential energy. So because it's above ground, it has energy. And since it has the ability to fall back to its original position, it has the ability to transform that energy into kinetic. So the same is true for a molecule, or 2 molecules, or 2 atoms. When the 2 atoms are close to each other, their relative potential energy is low. But whenever you add heat, you can move these 2 atoms away from each other. And therefore, because you change their relative positions with respect to each other, you've increased their potential energy. So let's say if you cool it down, these two can come back together, forming this molecule again, releasing heat energy. So whenever you change the phase of a substance, you change the relative positions of the atoms and molecules. Thus, you change the potential energy. The same way as if you move a ball from the ground, if you lift it up, you're changing the potential energy of that ball. Now it has the ability to fall. Likewise, if you separate two atoms or two molecules, now it has the ability to come back together and release energy as it does so. But to separate them requires the input of energy. So anytime there's a phase change, you're changing the potential energy. So when a solid goes to a liquid, the potential energy increases. When a liquid goes back to a solid, the potential energy decreases because the atoms are coming back together. And whenever you raise the temperature of something, the kinetic energy of that substance goes up. Let's try this problem. How much energy is required to heat 7.5 kilograms of ice from negative 30 degrees Celsius to steam at 200 degrees Celsius? What do you think we have to do to find the total energy? Well, let's go back to the heating curve. There's something that you need to understand. Now, there's 5 different Q values that we need. The first one is to heat up ice from negative 30 degrees Celsius to 0. And that's a temperature change problem. So we have to use Q equals MCAT to get that answer. Now, the second thing we need to do is heat up ice to liquid water. So basically, we got to melt ice. That's Q2. That's a phase change. So we need to use M times L to get that answer. And then we need to heat up liquid water from 0 degrees Celsius to 100. That's Q3. And then we need to vaporize liquid water into steam, which is Q4. And then we need to heat steam from 100 to 200 degrees Celsius, which is Q5. So be careful with these problems because you have multiple Q values. Let's start with Q1. So let's see how much energy is required to raise the temperature of ice from negative 30 to 0. So we're going to use the equation Q equals MCAT. The mass is 7.5 kilograms. The specific heat capacity of ice is 2100. And the change in temperature going from negative 30 to 0 represents an increase of 30 degrees Celsius. So this is equal to 472,500 joules. So now let's move on to Q2. The equation is M times L. The mass is 7.5, and the amount of energy required to melt ice, the latent heat of fusion, that's 3.33 times 10 to the 5. So it's going to take 2,497,500 joules just to melt the ice. Now let's move on to Q3. Q3 is a temperature change problem again. We're heating liquid water from 0 to 100. So it's Q equals MCAT. So we have the mass, the specific heat capacity of water, which is 4186, times an increase in temperature of 100. So this is equal to 3,139,500 joules. Now Q4 is a phase change. So it's going to be M times L. It's the mass of 7.5 times the latent heat of vaporization, which is 22.6 times 10 to the 5. And this is going to give you 16,950,000 joules. As you can see, the majority of the energy is going to vaporize liquid water. It only takes a small amount of energy to heat up ice, but it takes a lot, or a huge amount of energy to vaporize liquid water into steam. This explains why sweating is so effective for the body to cool itself down. So whenever you're exercising a lot and you sweat, That's the body's way to efficiently remove heat from your body. As you can see, a lot of energy goes to vaporizing a liquid into steam. Now, what about Q5? So that's the energy required to go from 100 to 200 degrees Celsius while water is in the vapor phase. So we need to use this equation again. The specific heat capacity for steam is about 2010, and the change in temperatures is positive 100. And so this is equal to 1,507,500 joules. So now we can calculate the total energy, which is the sum of Q1, 2, 3, 4, and 5. So let's add these 5 numbers. So if I typed everything correctly, the total energy is 24,567,000 joules. However, more than half of this energy was used to vaporize liquid water into steam. So it takes a lot of energy to do that. Now let's try a calorimetry based problem. So let's say if we have a beaker and it contains water, and the temperature of the water is initially at 21 degrees Celsius. We're going to drop in a piece of metal, which is at a very high temperature initially at 150 degrees Celsius. So what's going to happen? Heat likes to flow from hot to cold, so heat is going to flow away from the metal into the water. So the temperature of the metal will decrease and the temperature of the water will increase. So therefore the final temperature is going to be somewhere between 21 and 150 degrees Celsius. And we know what the final temperature is, 27. The fact that it's closer to the initial temperature of water tells you that the specific heat capacity of water is much higher than that of the metal, particularly if the masses of the two are about the same, because you need to take that into account. But the mass of water is smaller than the mass of the metal, and yet the temperature of the water, it experienced a smaller change compared to the temperature of the metal. So the heat capacity of the metal must be very, very low. Now let's find out what it is. Now, according to the laws of conservation of energy, the heat energy gained by the water must equal the heat energy lost by the metal. So we could say Q of the metal is equal to negative Q for the water. The reason why we have the negative sign is because for the metal, it lost heat, and for the water, it gained heat. So one of the Q values is positive, the other is negative. This additional negative sign negates the negative Q value of the other substance. It really doesn't matter where you put the negative sign. You can put it on the left side or the right side. You will get the right answer. However, if you don't put the negative sign, it's not going to work out. You're going to have issues solving this problem. So let's begin. Now, we're not dealing with a phase change. We're only dealing with a temperature change. So we could say the MCAT value of the metal is equal to negative of the MCAT value for the water. Now, we do know the mass of the metal. It's 0.24 kilograms. I'm going to need more space, so let's get rid of that. We're looking for the specific heat capacity of the metal. And we know the final temperature of the metal is 27, and the initial temperature is 150. Now the mass of the water is 0.15, the heat capacity of the water is 4186, and the temperature change of the water, final minus initial, 27 minus 20. So notice that this value is negative, and this value is positive. A negative does not equal to positive, so by adding this negative sign, they are now equal. Now let's do math. So let's multiply negative 0.15 times 4186 times 7. So on the right side we have negative 4395.3. On the left side, 27 minus 150 is negative 123 times 0.24. That's going to be negative 29.52 times C. So now let's divide both sides by this number. So negative 4,395.3 divided by negative 29.52. You should get a specific heat capacity of 148.9 joules per kilogram per Celsius. So as you can see, the specific heat capacity of the metal is significantly lower than that of liquid water. So what that tells you is that the temperature of the metal changes a lot more than the temperature of the water. Notice that the temperature of the water, it was relatively constant. It didn't really even move much. But the metal went from 150 to 27. So what this means is that substances with a very low specific heat capacity typically experience a very large temperature change. And the substances that have a very high specific heat capacity experiences a small temperature change.